Okay, we're doing a chi-squared goodness of fit. During the last rating period, the percentages of viewers watching several channels between 11 p.m. and 11:30 p.m. in a major TV market were as follows: WDUX 15%, WWTY 19%, WACO 22%, WTJW 16%, and other 28%. Suppose that in the current rating period a survey of 2,000 viewers was taken and the results were recorded in the table below. Test to determine whether the viewing shares in the current rating period differ from those in the last rating period at a 0.1 level of significance. What do you conclude? I'm trying to test to see if the viewing shares have changed. So when I set up my null and alternative hypotheses, my null hypothesis will assume that they haven't changed. And I will run the typical hypothesis test to see if the collected data is strong enough evidence against the null to reject it and therefore prove that they have changed. So again, I'm trying to see if there's evidence that the viewing shares have changed, and I will assume they haven't. In other words, the percentage of the viewing audience that's watching WDUX, I'll call P sub x, is 15%. That was the last time that the data was collected, and we'll assume that it's still that 15%. And for the next one, WWTY, I'll call that the viewing percentage P sub y, and I'll assume that hasn't changed, that it's still 19%. And for WACO, I'll call that the viewing percentage P sub 0, and 22% was from the last rating period. I'll assume that hasn't changed. And then WTJW, so I'll call that P sub W, and that was 16%. And then the percentage that's watching some other station, I'll call P sub R, and that's 0.28. So I'm trying to see if there's evidence to show that that has changed. So the alternative is basically not as above. In other words, these aren't the percentages now. These are no longer the percentages. So that's my setup, and a sample of 2,000 was taken, and we have some observed frequencies now that are given. And let me go ahead and put that table here. So I've brought the table into this, the sample of size 200 and the observed frequencies. So these are basically the observed frequencies. And I need to calculate the expected frequencies. And how would you do that? Well, we had a sample of size 2,000, and in our last rating period, WDUX had 15% of the viewing audience, so we would expect out of our sample of size 2,000 that 15% of those, if there's nothing that has changed, should be going to WDUX. But when I take 2,000 and take 15% of it, that turns out to be 300. So I would expect that out of our sample, if the 15% has not changed, we would expect to see 300. What we actually observed was 182. Now for WWTY, we took a sample of size 2000, and we would expect to have seen, if nothing's changed, 19% of that sample go to WWTY. Now that's 380. So that's what we would have expected to see. Well, we observed 536. So again, there seems to be a little bit of a difference there. Going on for WACO, we would have expected 22%, which is 440. What we observed from our 2000 sample was 354. WTJW, we would have expected to see, if the null is correct, we're assuming the null is correct, we would expect it to see 16%, or 320. What we saw from our sample was 151. And then lastly, out of our sample of size 2000, 28% we would have expected to go to other stations. And that is 560. What we observed was 777. So in an estimating way, it looks like other stations have increased, and some of the other ones have decreased, although WWTY seems to have increased some. But again, I'm trying to test to see if I can show that these percentages have changed. I'll assume they haven't. I'll do this by taking this sample evidence and seeing if it's strong enough to get it to allow us to reject the null hypothesis. I need to compare the observed and expected frequencies and somehow measure the difference in these values. And that's what chi-squared does. So I'm going to calculate my test statistic chi-squared. And the formula for that is I'm going to go from the very first percentage, I equal 1, up to k. And k in our case is 5. K is equal to 5. And the formula would be the observed frequency, subtract the corresponding expected frequency, that difference squared, and then divided by the expected frequency. So starting with the WDUX, my first percentage there, I'll take 182, subtract 300, square that, divided by 300, the expected. And then I'll take 536, subtract 380, that difference squared, divided by the 380. 354, just working right across each station there, trying to compare the observed frequency to what we would have expected if the null was true. And then lastly, 777 subtract 560 squared over 560. And if I add those all up, I get a very large number, 300.61. Now I want to go look at the chi-square distribution. I'm going to look at my level of significance is 0.10, and I need to calculate my, or find in the table, my critical value. And so looking at the chi-square table, now my degrees of freedom is k subtract 1, so my degrees of freedom is 5 subtract 1 equal 4. So I need that value in my table, and looking in column 0.10, I get a critical value of 7.779. So I'm going to reject H sub 0 since 300.61 is greater than 7.779. Now, that just means that this value is way, way, way down there. 300.61 is so far to the right that it is not within the distribution that we would have expected, given that the null is true. So there must be something wrong with that null hypothesis. So I'm definitely going to reject it. The other thing I could do is talk about a p-value, but the p-value, anything less likely than that, is practically zero. So I can pretty much say that the p-value is zero. Always compare the p-value to the level of significance, and again, I will always conclude the same thing regardless of how I'm running the test. And I would say yes, a big yes. The viewing shares have changed. In other words, I've rejected the null hypothesis. So I'm basically saying that they have changed. They're not as stated in the null hypothesis. Now notice that I'm not telling exactly where those changes are, although I can look at the table and maybe draw some things from it, just the collected data, now that I know that that sample data is strong enough to get the rejection. But all I'm proving here in general is that the null hypothesis is not true, that there are some differences. Things have changed.